All right, today we're tackling a classic problem from Irodov's famous collection. Now, this one is a fantastic workout, really gets you thinking about the difference between mean power and instantaneous power. So let's dive right in.
So here's the setup. Problem 1.127. We've got a block, it has some initial speed, and it just slides on a flat surface until friction brings it to a complete stop. Our job is to figure out the power developed by that friction force, but in two very different situations.
So think about it like this. The block is definitely losing energy, right? It's slowing down. But is it losing that energy at a constant, steady rate, kind of like a slow, consistent leak? Or is the rate of energy loss changing over time? Maybe there's a specific moment where it's losing energy the fastest. Well, that rate of energy loss, that's exactly what power is. And that's what we're here to figure out.
Okay, let's start with part A. This is the more straightforward case. We're told to assume that the friction coefficient, mu k, is just a constant. It doesn't change. So the friction force is the same the entire time the block is sliding. Our goal here is to find the mean, or the average power.
Before we start plugging in numbers, let's be crystal clear on what mean power actually is. It's the big picture view. It doesn't care about what's happening from one second to the next. It's just the total amount of work done by the friction force, from the very beginning to the very end, divided by the total time that whole process took. Simple as that.
Look, the best way to approach any physics problem is to break it down into manageable chunks. So here's our game plan. First, we're going to calculate the total work. Next, we'll find the total time of the motion. And finally, we just divide the work by the time. See? A clear three-step plan. Let's get to it. Okay, step one is work. And your absolute best friend for this kind of thing is the work-energy theorem. It's a huge one. It just says that the total work done on something equals its change in kinetic energy. Well, the block stops, so its final kinetic energy is 0. The work done by friction, then, is negative 1/2 mv0 squared. It has to be negative, because friction is taking energy out of the system. On to step 2, finding the time. The friction force is pretty simple. It's just the coefficient k times the normal force, which on a flat plane is mg. Now from F equals ma, we can see the acceleration is minus k times g. And please do not forget that minus sign. It's a super common mistake. The block is slowing down, so the acceleration has to be negative. Once we have that, we can just use a basic kinematics equation to solve for the time t.
All right, step 3. This is the easy part. We just put all our pieces together. We take the expression for work we found in step 1, and we divide it by the expression for time we found in step 2. After you clean up the algebra a little bit, you're left with this nice, clean expression for the mean power.
And now for the final answer. The problem actually gives us numbers for mass, the friction coefficient, and the initial speed. So we just plug those values into the equation we just derived, and boom! The mean power is negative 2.0 watts. That means, on average, friction was draining 2 joules of energy from that block every single second.
Great! Part A is done. But physics problems love to throw a wrench in the works. So what happens if friction isn't constant? Let's check out part B. Now the friction coefficient actually changes as the block moves. It gets bigger the farther the block travels. This changes things a lot.
So you can see the difference here. Part A, constant force. Easy peasy. But in part B, because the friction force depends on the position x, the force is always changing. And if the force is changing, the acceleration is changing. Our old method from part A just won't work. We need a more precise tool. We need to think about instantaneous power.
Instantaneous power is exactly what it sounds like. It's the power at one specific moment in time. Think of it like a car's speedometer for energy transfer. The formula is the dot product of the force and the velocity at that exact instant. Since friction always pushes in the opposite direction of velocity, this just simplifies to negative F times v. This is the tool we need to find the maximum power. So the question is asking for the maximum instantaneous power. This is a classic optimization problem, straight out of a calculus class. Our goal is to create a function for power and then use calculus to find the absolute peak of that function. So where do we start? Well, we need to figure out how the block's velocity changes with its position, x. And guess what? The work-energy theorem is going to save the day again. But since the force isn't constant, we can't just do force times distance. We have to use the integral form. Work is the integral of the force with respect to position. So we set up our integral for the work done by this new variable friction force. We integrate from the starting point, 0, up to some random position x. Once you solve that integral, you just rearrange the equation a bit, and you end up with this really nice expression for the velocity as a function of x.
Okay, now we can finally build our power function. We know the force is getting stronger as x increases, and we know the velocity is getting smaller as x increases. So we just multiply them together to get the instantaneous power, p, as a function of x. And yeah, I know it looks kind of messy with that big square root in there, but this is the function we need to find the maximum of. Now, we could just take the derivative of that messy function, but dealing with that square root using the chain rule is just asking for a headache. So here's a pro tip, and this is super useful. If you want to maximize a positive function, you can just maximize its square instead. The x that makes p a maximum is the exact same x that makes p squared a maximum. And this little trick completely gets rid of the square root. It makes the math so much easier.
So we square our power function, and we get this much friendlier-looking polynomial. See? No more square root. Now it's just a standard calculus problem. You know the drill. Take the derivative with respect to x, set that derivative equal to 0, and then solve for the x that makes it happen.
Okay, after we do the algebra, we find the exact position, x, where the power hits its peak. But, and this is a classic trap, so watch out, the question asks for the maximum power, not the location. So we have to take that value of x and plug it back into our original equation for p of x. A bit more algebra, and we arrive at our final answer. And there we have it. We've solved both parts. But let's not just close the book and move on. It's always a good idea to step back for a second and really understand the story these results are telling us about the physics of power. This table really sums up our whole journey. For part A, the force was constant, so we could get by with just basic algebra to find the mean power. But in part B, that variable force threw a wrench in things and forced us to pull out the heavy machinery of calculus to find the maximum instantaneous power. The physics of the problem tells you which mathematical tools you need to use.
So, what should you take away from all this? Well, first, really understand the difference between mean and instantaneous power. Second, never forget how useful the work-energy theorem is. And finally, see how calculus isn't just for math class. It's an essential tool for finding maximums and minimums in the real world. If you get these concepts down, you can handle almost any problem they throw at you.
And that's all for this one. But I want to leave you with a little challenge to chew on. We found the position where the maximum power happens. But can you find the time it takes for the block to reach that point? You'll need to set up another integral using that v of x function we found. It's a fantastic exercise to make sure you've really got this down. Give it a shot, and thanks for watching.